you should be seeing a funky editor with some circuit and gates and stuff like that. And what I love about this is that I can actually, I do have annotation tools in here as well. Let me just quickly check. Yeah, that's perfect. Because that's kind of really close to what I do as well when I do the videos. How many of you are familiar with Grover's algorithm, first of all? Just because if not, I mean, one of the things that I wanted to go through before I dive into sort of exploring the algorithm, which is what I wanted to do today with you, is, first a little bit through the tooling that I'm going to be using, because I'm not going to be coding. I'm going to be using what you see in the screen, which is basically a visual quantum circuit editor called Quirk, which is done by, that's not my work, so this is done by a guy called Craig Gitney, who runs this blog called Algorithmic Assertions, and he's got a load of content in here about quantum stuff. A disclaimer from his side, he's actually joined the Google quantum team, but the tool still remains independent. So this is something that's in GitHub as well available, can be forked, it's open source. And indeed, actually I use it, I do have a version of this myself that I'm using to play some puzzles with guests on the channel. But yeah, don't want to talk too much about this. Is everyone more or less familiar with the concept of Grover's algorithm?
If you are comfortable with it, go ahead, give me a thumbs up reaction.
Can I see the thumbs up? Anyway,
I'll give you a number here in a minute.
Cool.
1, 2, 3, 4, 5. So 5 of us, if asked what Grover's is, we could respond. So 5 out of, what have we got here? 18, so.
Okay, cool. We'll build
1/3.
We'll kind of, it's a basic idea. So we'll build it from scratch, and then we'll kind of tear it apart and try to understand what's the intuition behind the algorithm. That's kind of one of the things that I usually do in the channel. So, and if I go too fast and someone is getting lost, let me know, stop me at any time, and I'll try to explain or rephrase whatever I'm trying to say. So, but first, quickly, so you can just get familiar with the editor, because there's a bunch of stuff in here that can confuse people in the first place. It's not something that, it's not a fancy IBM Q composer where you have everything really nicely designed. So, but it kind of, the look and feel is what you're going to see for the next hour or so. So you've got the editor in here. So you have always 2 qubits, but you can drag and drop gates, and you can add qubits as you go. And what you can see is that what the editor is doing, that we'll be talking about this in this session, is that it's got some measurement or some displays at the end here. The first displays are change displays, so they show you whether this qubit is on or off, or also with which probability, right? So they assume the qubit has been measured, and if I, for example, use a Hadamard gate, which you might be familiar with, you know that you get into superposition, and so you kind of have a 50-50 chance of getting a 1 or a 0. So this little square here is showing you 50%. So that's what it says. You've got a little block sphere as well to kind of tell you in which point in the block sphere you are, and you've got a bigger amplitude display that lets you take a look at the system as a whole, which is a key element when it comes to understanding Grover's algorithm. So there's there's different ways you can take a look at a circuit like this. You can take a look at the individual qubits and their probabilities, but you can also take a look at the system as a whole and see, okay, so this is the amplitude of, or this is the probability of the state 0, 0, the probability of the state 1, 0, 1. You can see they're empty. And what those little circles mean is, so you can see the square is half full. So it means it's got 50% of measuring 1, 0 if we measure the whole system. And this little bar you see here, it's a phase indicator. So it's telling us the phase is 0 degrees. You will see that if I have 1 qubit and I apply a Z gate, which if you're a bit familiar with what this combination of gates does, is it flips the relative phase of the one component to 180 degrees. And you can see this here and in the square that represents 0, 1. Now this is a bit difficult to read sometimes, because it's not like you don't have a bar plot. That's what you typically see in some circuit editors with all the different output possibilities. You have this little guideline here, this little hint that tells you this is for the state 0, 1. And as you can see in this this information, in this dialog box that pops up, there's a phase of minus 180 degrees. And what's great about Quirk is that you can place those displays in between your circuits. So you can kind of inspect the circuit as you go. It's something that obviously you can only do because it's a simulator, so you cannot really do this in a real quantum computer, but it's going to help us understand what's going on inside the different steps of the algorithm. I really highly recommend that if you're interested in quantum computing and quantum programming, you play with this. It seems a bit overwhelming at the beginning, but it's a great tool for learning, because it also has spinning gates, which is a non-standard type of gate. So what this does is it simulates the evolution of the gate with time. So it allows you to understand, okay, so if I apply a Hadamard gate in here and I apply a spinning Z gate, it spins through time. You can see how the block sphere moves. So it's that's not what you can do with a quantum computer, obviously, but it's just a learning tool that tells you, okay, so this is the effect of this gate in time. And then it has a bunch of built-in things in here that we won't be touching, but it has like built-in Fourier transform gates. It has modular arithmetic that you can use to build a small version of Shor's algorithm. So I highly recommend this as well. You guys play with these. If I refresh the page, so this is the way this looks like when it starts, and you can actually take a look, and it even has some example, circuits that you can take a look and, for example, take a look at quantum teleportation. So here, the editor is using some dynamic gates to show you how the message is going from this qubit to this qubit. So you can see the block sphere rotating the same way. But that's just so you know a little bit about the tool. You can make a lot of fancy stuff with this, but we won't be getting really crazy with this today. So far, all good. Let me clear this all. Good. So let's first talk about Grover's algorithm a little bit. Grover's algorithm is a search algorithm, or that's at least the way that is most commonly introduced in the literature out there, in books and on the internet. The idea of Grover's algorithm is that you start with a superposition. We'll just stay at 2 qubits, and basically those are the 4 elements that your superposition can represent: the 0, 0, 0, 1, 1, 0, and 1, 1. And the algorithm is supposed to help you search that one particular element that you're looking for in a way that is, it's not exponentially faster than with a classical computer. It's, I think, something around the, I don't know if it was quadratically faster or something like that. I'm not really up to date with the terminology there and with the actual performance, but it's not one of those wow improvements, but it's definitely something that works faster than in a classical computer. Now, what the algorithm does, we'll build it quickly. It's built basically, it's got 2 main components. One component is what a lot of people call the oracle. I find it a bit misleading, but the idea is the oracle is the box in the algorithm that helps you flag, so to say, the item that you want to look for, right? So we're going to build a really basic box right now. Let's say that, let's assume we want to find the element 0, 1. So this box, and I'm going to just build it right away without explaining what I'm exactly doing, because we'll dive into this in a second. So we'll basically, or let's do 1, 0, because it's easier to implement. So this is just this is how the oracle looks like, and then the second box that is the part of the algorithm is what's called the amplitude amplification. So now that we have the element that we want to find flagged, and you see that the flagging is happened at the phase level, right? So you see all the elements have a phase of 0 degrees, and this element has a phase of 180 degrees. So the next part of the algorithm is what is basically amplifying the amplitude of this element, right? So we're going to go ahead and build it. So does something like this, right? So it's got a layer of watermarks, then control nodes, and this here. And with grid, you can also, I think I can also copy a whole column. Yeah, so you can see at the end of the algorithm that what you get is if you measure the circuit, you're 100% of the times are going to actually find the element that you're looking for. And I know that this seems a bit stupid because, as I said, this is the, let's see if I can draw. So this part here is the oracle, or is the flagging part, and this part that follows this whole block in here is the amplitude amplification, right? So, but obviously you saw that what this element is doing is actually, you know, I'm assuming, or it assumes I know what I'm looking for, right? So if I know what I'm looking for, what's the point of the whole story? This is just an example to introduce the algorithm. So the idea is that black box in here, so that's something that it's problem specific, right? So it's something that you're going to have to adapt based on the problem you're trying to solve. I mean, you're not just searching usually stuff because you want to search for stuff just for fun, but there's some you know, goal behind this, right? And I'm going to see if I can give you an example of these. There's one common usage of this algorithm is to find solutions in a brute force way, so to say, right? So in combinatorial problems where you have to try a lot of different combinations of things, you can use Grover's algorithm to find a solution. For example, the graph, how's it called? So I have here the max cut problem, right? So this is a paper that explains how to solve the max cut problem with Grover's algorithm, and with a version of Grover's algorithm that works in machines that already exist now. So the max cut problem, and I'm not going to go too deep into this, it can be simply explained in terms of coloring a graph, right? So if you have a graph like this one here, the max cut problem says, well, give me a combination of colors. You have two colors to pick, right? Blue and red. So give me a combination of colors that basically cuts through the most amount of edges, and I'll explain that in a second. Let's make a simpler graph. Let's assume that we have a graph that looks like this, right? So it's like a star, right? So, well, it's actually this is actually a star graph, so I don't really need to draw it again. So here you have, it's almost a star graph. Okay, it's not, so we can forget about this one. So you have this graph in here, right? So obviously the solution to this problem is if I paint this element, this node red, and then I paint the other nodes blue, right? So this is the best solution to the problem because there are exactly 3 edges that have different colors at each end of the edge. So that's the goal of the problem, is to find a coloring composition that maximizes the amount of edges that have 2 different colors at each side. And, you know, as you can imagine, if the graph grows and grows and it's not that simple, that becomes really complex. And one way to approach this problem is, well, why not take a look at all the possible combinations of colors and just, you know, brute force the problem and look for this. But obviously, if the graph grows and grows, the possible combinations of zeros and ones, if you think that the blue is a 0 and the red is a 1, for example, if we encode it this way, you know, and I say, look, my graph is going to be basically a string of zeros and ones based on what node I color with each color. Well, the number of possibilities is going to grow exponentially, and so it becomes quickly intractable. The idea of Grover's algorithm is, you know, you can actually try to solve such problems if you know sort of a smart way to encode this problem into your Oracle function, right? And what this paper proposes here, and I'm really not gonna dive into this more than that, just to show you what are other, by the way, if anyone's asking any questions, on the chat, because I don't know if I have any, I don't know if I have the chat open.
Nothing we can't handle. We just got the URL for it. That's all, for the paper. We're good.
Yeah, no. But I mean, if anyone has any questions, like in the Zoom, let me just. Oh yeah, okay. Amir. Also, Amir is in here. Hi, Amir. So the idea here is basically that. Let me go back to what I was doing here, right? So yeah. So no, sorry, to the paper here. You can encode, you could encode the Oracle, so that's kind of a bit the explanation that I gave right now. But you could think of an Oracle that kind of counts the amount of differences and different edges and colors, right? So for example, if you have a I'll go here. So if you have the circuit, I'll clear, I have a bunch of other circuits free here to use, so I don't have to create new ones. So let's assume that we have a, so that's node number 1, that's node number 2, node number 3, and we'll keep it like this small, right? So you have 3 nodes. So if you encode each node with a qubit, right? And you say, you know, I'm painting these red and I'm painting the other ones blue, right? So I can easily say, okay, node number 1 is red. We said red is 1. 2 and 3 are blue, so they are 0, 0. So that is my solution, right? And all the possible combinations of colors are really 8 because you have 3 qubits. So that can easily be represented with a superposition. So if I start with a superposition here, and I'll show you what the amplitudes are, you can see that each element of the amplitudes can be one possible solution. So a way that you can use the Oracle to help you solve this problem is to say, look, there are edges between the qubit 1 and qubit 2, and there's an edge between the qubit 1 and the qubit 3. So I can, you know, I can try to use a technique like, for example, you know, using a control node or something like that. I'm not going to get too much into detail here, but you can use a technique like this to then say, okay, so if let's assume this is qubit 1 for the sake of the example, and I use a control node in here. Basically, what I'm saying is, if the possibility of so if qubit is if qubit 1 is if qubit 1 is 1, right, this control node will be activated, and so it will flip the qubit 2, which if the qubit 2 was 0, right, it's gonna basically turn it into a 1, right? And so what I can apply now is I can apply a Z gate, and what this has done is it has shifted the phase, right, of all the elements in my superposition. I don't know if you can see that well, that actually have that particular pattern, right? So you can basically build your Oracle in a way that actually flags the elements of your problem that are relevant to you. Yeah, I don't know if I explained myself really well, but this is the Roth idea. So for the rest of the session, we're going to be using a dump Oracle. So we're just going to be you know, assuming we're going to flag one element 1, 0, and that's it. But you can. This is where you encode the logic, or the thick and the meat of your problem is encoded in how you build the Oracle. I hope that I have at least made it clear enough that it's not just a dummy, let's find one element and that's it. So, okay. The next block that we see in the algorithm, so we said, okay, this is the Oracle, and for the Oracle, we're just going to assume believe me, this gate flags the element 1, 0, and we're going to assume that's it, and we don't care about any particular problem. So now we want to find that element, right? And the next piece in the whole story is amplitude amplification. So this is kind of where my journey with Grover's algorithm started, because when I was taking a look at this algorithm and I was trying to understand how this works, I basically found myself reading something like this, right? Which it's not necessarily bad, but it was for me a bit of a sort of a shock. I was not kind of ready to now go one level, up in mathematical terms, and kind of try to understand. Okay, if we represent our state as a vector, and then we do, the oracle is kind of shifting the vector a little bit, downwards, and then we apply a mirroring operation, which kind of, it was a really mathematical explanation that is really interesting and actually nice to go through, but it didn't really come across as, it didn't really resonate with me, right? As in, like, as someone who is a bit more coming from a pure programming sort of more the kind of script kiddie kind of person that's just Googling pieces of code here and there and gluing things together, I was like, how could I how could I have come up with something like that? What's the sense in this? Is this just someone, you just do the math and come up with the gates, which is kind of, one way to approach a problem, or is there a more intuitive way to understand how this works? And that's kind of how I got into sucked into the problem, or sucked into the algorithm to kind of try to understand what's going on in here, right? And one of the first things that you kind of see is that if you start placing an amplitude display in here, you can see how this evolves with time, right? So we have here our amplitude amplification, our oracle has had effect now, and we have one element that has a phase of 180. If we place another display after the Hadamard layer, I mean, to be honest, already at that point, it's a bit confusing, right? We don't really understand, or I'm not really like good at finding a pattern here in terms of, yeah, it's shifted something, but if my oracle does something else, like flagging this element, it's going to do something else. And then I don't understand really why those X gates need to be here at all. So, it's kind of confusing. And I think one of the most illuminating discoveries for me was to understand the concept of interference at the smallest level possible, right? At the 1 qubit level, because everyone talks about interference. Everyone says, yeah, quantum computing is about interference. And it's about kind of, a bit like composing a piece of music and figuring out the right way to interfere the right answers with the wrong answers, and the wrong answers with other wrong answers, and then finally getting to your solution. But you really never talk about interference, or you never really see anything in practice about interference. And for those who might be thinking, what am I talking about? So that qubits, or a quantum state is kind of represented with something that is, it's a bit of an equation of a wave in the sense that you have amplitudes and phases, right? And you can think of, in a really naive way, that you have your state 0, right? And that this is a wave. I'm just going to draw a wave, which I hope that's not going to be horrifically bad in here, but imagine this is a wave, right? And so what interference is that if I would have magically another 0 coming into this picture, which has another wave that is perfectly in phase with this one, right? This means the peaks are aligned and the valleys are aligned. So these two waves interfere constructively. That's one way to talk about this. They interfere constructively, and they just, when you put them together, they just become bigger, right? So I don't know how to draw it here, but the peaks are bigger and the valleys are deeper, and so on and so forth, right? Now, if you okay, yeah, exactly. So what happens though if this wave in here, instead of being completely in phase, is a little bit out of phase? Maybe not a little bit, but it's, you know, what happens if the peaks of one wave comes in really nicely? So if we assume that the Hadamard gate applied to a state that is composed of a 0 wave and a 1 wave, right? This is the same as this gate being applied to this state plus this gate being applied to this state, right? So you basically have a Hadamard applied to 0 and a Hadamard applied to 1. And we know what those elements are, right? So we know that that this part will basically unpack into a 0 plus 1 state, and that this part will unpack into a 0 minus 1 state. And now this is where you see interference, right? This is where you see that 0 and the, with the 0 and the 1s, right? It's just dual, right? Screen sharing, yeah, exactly. So that's kind of the same, right? So if we follow this idea, then, you know, you could just think of, okay, so if I follow up the example, all I need to do is I need to minus this entire box in here, right? So this is a plus, would be a minus, this is a plus and will be a minus, this minus turns into a plus, and this minus turns into a plus, right? Now, something really interesting just happened, because if you now apply the interference rules, right, you will realize that this very action of the oracle has broken these beautiful balance that we talked about. Now the elements 0, 1 and 1, 0 and 1, 1, sorry for the typo here, they are not canceling anymore, right? Because they're not perfectly balanced. The 0, 1, right? The zeros kind of stay the same, because there's a plus, there's a plus, there's a plus, and there's just a minus, right? So overall we stay with plus, right? With plus 0, 0. But with the other elements which were disappearing, they don't disappear anymore. So the 0, 1, it's a plus in here, it's a minus in here, so they cancel out. But it's another minus in here, and it's another minus in here. So actually we end up staying with a minus 0, 1. And we can do the same with the other ones. 1, 0, it's positive. 1, 0, it's positive. 1, 0, it's positive. So there's an overbalance on the positive side of things, so that stays positive. And with a 1, 1, the same thing happens, right? So 1, 1 is positive, 1, 1 is negative, they cancel out. 1, 1 is positive, 1, 1 is positive. We end up with a positive balance. So what does this look like? So now it's not a 0 anymore. It's not like the 0, 0 anymore. Those things haven't canceled out. And these looks awfully similar to this here, right? I don't know if you can see that, but the signs are the same with the exception of the 0, 0, right? And so this is a bit the kind of aha moment of, I don't know if you're starting to see how amplitude amplification works, right? So we have applied a Hadamard layer here that has done all this fancy, you know, work that I just try to draw here in a really messy way. But now, if we somehow manage to change this sign to be minus, right? Then we will basically have the state minus 1, 0, which is, it's kind of what we're looking for, right? We're looking for 1, 0, really. And so the obvious way, you know, an obvious way to do that is with this construction in here. That's the reason you need the X gates in the first place, because you cannot flip a phase with a control Z operation for like the 0, 0 state. It's the only exception if you, let's see if I have a free one here. So if you, I think I can't clear the screen. Yeah. Anyway, you can't really, where's Grover? Here. So you can't really flip the face of the 0, element, because the control Z will always, this Z will always expect this qubit to be 1, in order for this to be, for the face to flip. And so you sandwich it with a layer of knots to kind of create the opposite effect, which is flagging the 0, 0. And and then you're done. And then if you apply a Hadamard to these, you can again do the whole interference game again. But I mean, we know that it's, if we apply, we just saw before that we apply the Hadamard to a superposition that we, that's one of those 4, we're going to go back to that original element, or what I sometimes call the seat of the superposition. So this is basically going to take us to the 1, 0 that we see here. Really, I think I can clear that. Maybe let's just 1 minute pause for a second. Let that, because I probably said too many times 0, 0, 0, 1, 1, 0, 1, 1. Have you been able to follow somehow? Like, is it somehow clear? Do you have any questions, or was it all this just nonsense so far? Have I gone too fast? I tend to speak too fast.
Chime in, folks.
Yeah, that was good. Happy for you to keep going.
Hello, question. If the result of applying Hammergate is so predictable, what is the difference between traditional computing?
So the difference is that once you scale the number of qubits, this becomes untractable by a real computer, by a classical computer. So here, for 2 qubits, with 2 qubits, we are able to operate in a space where we have 4 possibilities, right? Now, think about 30 qubits, like 100 qubits or something like that. That really quickly, like 100 qubits is totally thinkable. Like Google has the Sycamore, I think it's pronounced Sycamore, has about 72, is it 72 qubits? And that's already, like, the closer to get to 100 qubits, these allows you to process an amount of the process. Maybe I want to be careful here, but this allows you to operate in a space that basically has more data than the amount of atoms in the universe. I mean, this is just the sort of the bizarre thing about this, is that your quantum computer scales linearly in terms of qubits, but exponentially in terms of the data that you can process. So if you think about the problem I talked before, the max cut problem, if you have a graph that has 100 nodes, which is not such a big graph. I mean, it's 100 nodes, right? But the problem is intractable by a classical computer, because you can't just go through all the 2 to the power of like 100 different combinations of zeros and ones that you could have. So that's the difference, right? Now we are playing here with just 2 qubits because it's kind of, it fits in a screen, right? And I can paint all these zeros and ones in here, and it looks kind of more or less nice. I don't know if that's answered your question.
Thank you, it does. Then the next question is that if the result is deterministic, even though the result is numerous, then what is the use of that?
So the fact that the result is deterministic in here is just a coincidence, because it's a really small, it's 2 qubits. With 2 qubits to get a deterministic result. If now we will scale that example to 3 and 4 qubits, and you will see that you don't get a deterministic result. So you basically have to sample a lot, and then you get a probability distribution, and you kind of hope that, so basically the element that has the higher probability is your solution, right, with high probability. And that becomes even more, if you try to apply Grover's algorithm to a problem that has more than one element that you want to find, not just one element, you can also do it. We'll take a look at this. Then this probability spreads even thinner quicker, right? So you really quickly we'll see that at some point it's really just almost, you've got like slightly over 60% chances of actually getting the result that you're looking for. So it's not all happy and perfect. It ends up with a lot of sampling in there. Yeah.
So what is the result you're looking for then? If you have less 2 to 72, 2 to the power of 72, you're talking about a huge number. What are you looking for?
I mean, that's the kind of, the algorithm doesn't tell you what you're looking for. It's the problem so this is just a tool to solve a problem, right? So I can only give you an abstract kind of problem with a max-cat, right? Let's say that for whatever reason, your chemistry problem can be reduced into mathematically into a search of a solution for the max-cat problem. So there you go, right? I mean, there you have a utility in terms of what you're searching. So you have this is not like, the problem with this algorithm is that people use the term search. It's not to be confused, with searching in a database or something like that. It's not like a query in Google, you're searching for something. It's about searching, in this specific example, searching for a solution within all your set of possible solutions. But that's just one application. I guess there are many other tricky ways or funky ways you can use the algorithm. So at the end of the day, this is just a way to amplify an amplitude inside your set of possibilities. And this is, it's used sometimes in other algorithms to exactly, just the amplitude amplification trick. It's kind of a primitive to build other quantum algorithms later on. If part of your algorithm is that you need a certain amplitude to get amplified, then you can apply that box to do that, that black box to do that. But at the end of the day, we'll kind of come down to whatever real world problem you're looking for. And that's something that I can't really, I mean, I haven't explored enough to give you more examples of problems, but it's definitely something that, I mean, we can do a quick Google search later if you want as well. That's also fun sometimes. What problems can you solve with Grover?
Okay. All right. Thank you very much. This is really helpful.
Yeah, you're welcome. So let's now jump into what happens when when we make the algorithm bigger, right? So when we are now scaling the algorithm, right? Well, and by the way, one thing that not a lot of people realize, and that's actually really funny, is that the same reason I just talked about, the fact that did I actually, oh wait, I can undo this, yeah. So I talked about this particular correction in here, right? That you have to make a correction to that 0, 0 state. Now, guess what happens if my initial state here is like 1, 1. So as you can see, the algorithm actually doesn't work anymore, right? And it's a bit funny because I never said about, I never mentioned about the initial state being something relevant at all for the algorithm. But that, like, I'm not finding the element that I want to find. I find the 0, 0. And so this is a key element to Grover's algorithm, or to amplitude amplification, is that that this part in here is something that depends on the initial state, because the correction that you're making, this correction of the 0, 0, so you get the state that you want, it's dependent on what state you started with, because that's kind of the state that by means of the principle of conservation of information is the state that kind of stays alive throughout the whole interference process. You start with the 0, 0, you have the 0, 0 in here, you have the 0, 0 in here. So this information is preserved so that you can come back to it, right? And if your initial state, and I'll clean this already for good. So if your initial state is 1, 1, and now I remove the X gates, because that's what yeah, and sorry, that was that's the original. I think I changed the oracle. So if I remove the X gates in here, and now I just, my amplitude amplification just becomes these 3 layers in here. Now I see that I find again my element, and this is because the element here, that's the correction, it's correcting exactly for the initial state, right? So this is a really important element. And this is kind of the same reason why the algorithm starts to break as you have more and more qubits. And we'll see this now in a second. So
Daniel, there's an important part about this, though, that I'm realizing this time around. What's cool about what you just did is if you start in that one state prior to your first Hadamards, you've actually reduced for each amplitude amplification, you've reduced the number of additional gates.
mm-hmm. Yeah.
It seems like that could be an optimization.
Yeah, totally. That's actually, yeah, I mean, again, you kind of reduce the amount of gates to the expense of having to prepare a certain initial state, which kind of at that point, I guess, depends on how well your machine is able to do that. But we've kind of removed 4 gates versus having to prepare 2 qubits in the one state, which there should be definitely a gain in here. You know how I discovered these? Because when I first started playing with Quirk, and I did like what everyone would reasonably do, is I saw that, oh, look at this, there's a Grover search implementation, and I look at this and I was like, what the heck is this, right? Where is my amplitude amplification here, right? And you can see, and I was like, why there are not gates at the very beginning, right? This is another type of display where you can see all the different elements of your superposition, and you can see in this example, that's a built-in example by Craig, that this particular element with each iteration increases in probability. And now we'll take a look at these in a second, right? But essentially what Craig is doing is using a non-standard control here that is an x-axis control. This x-axis control is the same as doing a Hadamard, a classical control, a normal control, and another Hadamard. So you're sandwiching these. And so he's kind of, from that perspective, saving 2 more gates. If you're able to tune your quantum computer the same way you can do it with the IBM Ambrock, for example, to you can fine-tune the pulses to implement your own versions of gates. If you could somehow tune the machine to natively implement this operation, then yeah, you're saving on depth, right? And on the depth of the circuit, and so that makes it even more friendly for existing machines that are become useless really quickly. So that's a good point. Yeah, thank you. Good. That's what you meant, right?
Yeah, and it was neat to see that Craig also did that. He initialized to all ones.
Yeah, exactly. That's
for that state before going to the Hadamards.
Yeah, it's one of those things where it was passing me forever because I was not like, I couldn't figure out why the heck is he going to the state 1 in the first place. So good. Now I think I've lost my, but we'll build it quickly again, no problem. So we had Hadamards, we had a control setting here, and we're now gonna just, so I'm now gonna scale these to, let's go like straight into 4 qubits, right? So for these, I just need to add, I just need to kind of make that bigger. We'll flag the state 1000, and I think I can just do these. And so here, as you can see, we have to extend the amplitude amplification to correct for the right state. So we're starting with the 40 state, and so we have to do the same thing here. And here we go. So now we can see that the state is like, you just have about 47% chances of actually hitting the right state that you're looking for, and so you have to sample many times to then kind of come up with the fact that this is the solution. As I said, if you want your oracle to flag more elements, you can also do so. So now let's do, for example, the 1001, right? So now we have at the end of the algorithm, and let me see if I can paint that. So this is the oracle, and this is amplitude amplification here. So you have now two elements. Of course, the probability is been reduced to now 39%, and so the more elements you have, you know, the more the less probability that you're getting. But you know, you kind of think about, well, until like what's the limit, right? At some point, this kind of has to break. And actually, another question that you would naturally think about is, how can I, like, is it possible to increase these probabilities even more if I, you know, repeat the same process again? And the answer is that yes, indeed. So if you, you know, if you, and now I'm going to create, I'm going to make two custom gates, right? So I'm going to make one custom gate that I'm going to call the oracle, and this is going to be, so with Krrig, you can select the like a portion of your circuit and make a custom gate that pops out here. So I don't have to, and this will be called amplitude amplification. So I don't have to kind of, you know, do the whole thing over and over again. And now I can just say, okay, so if I flag the same two elements again, now you can see that the phases have changed in respect to everything else. And I use amplitude amplification. Now we went from 39 to 47%. So we've increased that. And so you can keep going, and at some point, this is just going to break. I mean, it breaks already now. So you can see that with this extra iteration, we've just reduced the probability. And so you might ask kind of, you know, why, right? Why this happens. And if you think about the explanation, the mathematical or the geometrical interpretation that I briefly talked about in the beginning, what you will usually find is that you basically, if this is your desired target state where you have found your element with maximum probability, what you just did now with adding an extra iteration of the algorithm is you've passed you know, by the actual solution, and you kind of gone to another state that is not optimal anymore. So you've rotated too much, which was never somehow appealing to me either, but it mathematically makes sense. But the way you can think about this in terms of interference and everything that we've just done so far is the fact that, you know, you can take a look at what happens to the amplitudes after each iteration, right? So here we've done with the first iteration, and pay attention that the superposition we have, it's really similar to the superposition that we have right before starting. The only difference is that the amplitudes of these elements are higher, right? But the phases are the same, and I'm saying the same. I know they are all flipped 180 degrees, but remember that what really matters is how are they flipped in relation to the initial state. So if the initial state 0, 0, 0 is flipped 180 degrees and everything else is flipped 180 degrees, I can just as well remove that minus and it's the same, right? Physically speaking, that superposition or that set of phases is the same as this set of phases because they're all pointing at the same direction. So you kind of, you know, this is a playground for the same trick for the same interference trick to happen again. Now, because these elements already have higher amplitude, if we were to now expand again the whole interference chain of events, we will see that they will just be accumulating more and more amplitude because of the trick that we talked about. But what happens right before it breaks, right? So we said this iteration already breaks, right? So you see that at the end of the last iteration, the one that still works, this is not anymore the case. The phases here are not anymore all pointing at the same direction, right? So you should intuitively kind of know or suspect that this is the next iteration you're going to do is not going to work well because you don't have, well, because your amplitude amplification corrects for the seed of that superposition for 0, 0, 0, 0. And here, this is a superposition that is not the one from 0, 0, 0, 0. So your amplitude amplification is not going to work. One thing that I haven't explored yet that I want to do in a future video is, can you at this point in time change your amplitude amplification so that it corrects for the right state, and you give it another twist, right? My guess tells me that you really can't do that, but it's something worth exploring. But I wouldn't even know where to start, because if I just take a look at the different set of phases in here, like I would have to think, okay, so which is the seed? The seed of the superposition is non-trivial. It's probably actually another superposition. And so how do you conceptually or intuitively, how do you think about flipping the face of a superposition? So it's a bit awkward, and I'm not really sure whether you can pull that, you can stretch that more than these, but that's kind of the maximum where you can get at. And so this is basically what happens when you scale, right? And you can see the amount of the number of elements is also growing exponentially with the number of qubits, right? So actually I don't want to break that, but I think it only supports 16 qubits.
Daniel, to do what you said, if you apply the oracle to that state where the phases are going in the other directions, then it looks to me that they're all negative phases on the qubits, on the states that you don't want, except for the two which are the target states. So if you apply the oracle to that, it's going to apply a minus sign to those two, and then they'll all be pointing in the same direction.
Yeah, that's good. You're right. Let's see what happens. I haven't thought about this way. Of course. So give me a second. If I apply the oracle here, right? Now they're all pointing at the same direction. Look at this, interesting. So we've gone, okay, so what has happened is, it's probably, okay, so what probably happens is, which is what's unavoidable, I guess, is that this is the maximum amount they can accumulate. It's almost 50%, right? And so when you do the next iteration, you still see decrease, but it's a smaller decrease than we see before. So you've mitigated a bit the decline of probability, which is not bad. Actually, that's interesting. The trick is, okay, because basically the idea is those two numbers are so big already that when you do this plus minus thing where you cancel out stuff, then they just, I guess you would kind of cancel out in the wrong direction, right? I guess. But it's a good, okay, yeah. I'll definitely explore that.
Well, so if you think about it in the way that I think you don't like, so as in the geometrical viewpoint, then every time you apply the Grover operator, or in other words, a combination of the O and the AA.
I know where you're going. It goes a little bit backwards.
It rotates by a certain amount. And so when you come to your best answer, so as in the one you've got there, that's when you've rotated closest to the perfect answer. And then if you rotate again, then you go past that, and so you start going negative again.
Yeah.
So you can't easily improve on the answer you've got there.
Yeah, nice. I actually, one of the things that I'll definitely do is I'll try to do a really full detailed breakdown on the mathematical the geometrical interpretation, because I have never done this. I kind of gone through this and thought and kind of like told to myself I roughly understand what they're doing here, but I never felt comfortable enough, and maybe I should do that. I think doing uncomfortable things is what makes us learn more. So, but thank you. That's a really good point. Yeah, nice. And actually, this kind of takes me to the next point, maybe how much time we've got left. Okay, cool, still some time. Because, you kind of think about, okay, so as I grow the amount of qubits, right, if I have to be aware of how many times I have to operate or have to kind of repeat these. And I also want to know how many, maybe, elements I'm kind of looking for. That kind of depends. I think those two things really depend. It's not that they depend on each other, but the more elements you're looking for, the more stretched out those probabilities will be. So the more you have to repeat to get them up enough so that your sampling, works with a certain confidence, you're probably asking yourself, okay, how can I, like, is there a way that I can count upfront, or I can know upfront how many elements are flagged in there, so I know, whether, how, I know how to optimize the amount of iterations that I do and all this kind of stuff. And this is something that there's actually an algorithm for this, but there's a way that I've been recently exploring to attack the problem, that I don't know if it's really, correct 100%, but I wanted to kind of walk you guys through this as well, see what you think, because it's using what I've recently learned. It's called the Hadamard test, which, to be honest, I didn't know it was called the Hadamard test, but my intuition kind of came from the fact that, okay, maybe let me first try to do one thing. So I'll try to pack the entire algorithm into one black box, right? Into one gate. So so I will not start with the. I'm a bit unsure what I should consider the first layer of Hadamards, but we'll try to go with just the elements and yeah. Exactly. So I'll call these Grover with 2 elements, and because I'm one of the things that I let me see if I can follow. Let's add another element. Let's say let's remove one of the elements. So let's go back to these, and now I will create another gate with just 1 element. So that should be Grover with 1 flagged element. And we can even do one with like with 3 elements in there. So we'll just randomly pick 3 elements, and I will call this G3. Good. And I will just clean the whole thing. Oh crap! Sorry, I have to go back. Yeah. Clean the circuit, so because otherwise I'll lose the gates as well. So and I'll go back to we're using 4 qubits, right? So I'm going to keep one work qubit at the top just to show you what so intuitively what I was thinking about is that how can I, so I'm going to try to draw a bar diagram of like my superposition, and let's imagine that this is the probability of finding one of the elements that I want to find. The other ones are like fairly low, and there's another element in here, right? They're fairly low in here. So let's assume it's something like this, and it goes on, right? So what will be one of the things that I kind of realized is that if we were able to compare a run of Grover's algorithm with a run where nothing happens, and you have like just a uniform superposition, you could, or you should be able to, or you should be hitting these more often than these, right? Because you've got more probabilities piled up in here. So this is something that if you apply a Hadamard here, right, and you control Grover, say Grover 1, right? So what you're saying here is you're saying, okay, so now I have a state in here that is 50% chances of, being 1 or 0. And so I'm going to entangle these with an entire register that runs Grover's algorithm. And kind of, I thought, well, this somehow there should be something in here that should be able to tell me how many elements are here, because if now I have, roughly speaking or intuitively speaking, if I take a look at chance display, right? As I kind of said, you have if you can think of splitting these whole bar plot here in 2, right? And you should be able to have like for all. I think it's better if I use these as ancilla qubit, because then I get the leftmost qubit as being 0 or 1. Yeah, and basically it should be hitting more often on the one side of things. So if I take a look, let me see. I haven't played with these a lot. I just played with these a couple times, but I know because maybe it doesn't, because I keep, oh, wait a second. If I do these, exactly. So I believe there's a correlation between this number and the number of elements that Grover's algorithm is actually flagging. And maybe I did this wrong, that I just run one iteration, and I should kind of have packed it with more iterations in there. But if you control now with 3, it's kind of going down a little bit, right? So this is there's a funkier way to do this. There's with a full phase. So if there's an algorithm called quantum counting, I think that's the way it's called, quantum counting. And I think in the Qiskit textbook there's a really good explanation about this. That is basically kind of the idea that if you are able to figure out the global phase that Grover's algorithm that your black box has or is applying to your qubits, you're able to infer the angle somehow, the angle in which you're rotating. So you kind of, with these, you can come back to how many elements you have, your oracle is flagging. But I kind of feel like there's a simpler or a cheaper way to do that, this way.
Well, Daniel, so you're wanting to get a sense, like are you saying if you didn't know how many elements the oracle was tagging, you want to get a sense of the count?
Exactly.
So what I think I think if you just take the inverse of that last qubit, sorry, not the inverse. Yeah, I don't know if that would be the inverse, but like 100 minus 81.3. Yeah, the inverse. And then times 2 to the number of qubits minus your auxiliary bit. So that's 2 to the 4th. So it's 16. And then 18% of 16, maybe floor that. Floor that, and that would give you, what is that? 18.8 times 16. That gives you 3.
Okay.
So I think yeah, that would be the 3 elements.
So can you run that with 2? So if we do, so now it's 12%.
So 12.5 times 6.
Yeah.
12.5% times 16. That gives you 2.
Nice.
Yeah.
Yeah. I mean, it's kind of, intuitively speaking, actually, here's even better, right? Like you can see that you're hitting these more often. And so if you, intuitively, what I was thinking is that if I don't do the X, right, like the percentage of times this is on, or the other way around, because now I removed the X. So what I mean is let me see if like this now, okay, the bottom part. So it's definitely, that's why it's not 50%, right? Because it obviously goes here more often. Because if the intuition here is, if you measure a 1, it means Grover's algorithm took place. So it means you're hitting here. If it's 0, it means Grover's algorithm didn't take place, sort of in retrospect. So you're kind of landing on the other side of the wall of your superposition, and so that proportion should tell you something about the numbers. So, but I haven't, But actually, that you just okay. So you just basically calculated that. So I mean, at the end of the day, this thing here, it's kind of a bit of a 1 qubit phase estimation sort of thing. So it wouldn't be surprising that somehow has a relation, but I kind of find, I don't know, I found surprising, or I'm quite amused by the fact that you can figure out to do it in such a way. And I think I'm curious about how much accurate this is in terms of, like, do we lose accuracy if we're getting like more elements flagged in there or not? It shouldn't be the case, because take a look at quantum counting. I mean, it's a monster algorithm. That's definitely not, it's definitely not NISQ friendly. Like, I mean, you have to do phase estimation basically. So you have to apply, you know, exponential versions of Grover. Here you have to apply the inverse of the QFT at the end, and then you're getting still these, and you got to post process that to tell you the angle, and then the angle tells you the amount of qubits, that the amount of elements that are phased in here. Yeah. So I think that's I mean, it's a hell of a journey with just this little algorithm, to be honest. But I don't know, I think there's definitely a lot that I've learned in there that it's nowhere in any tutorial out there. And I've got basically a, you know, to be honest, that hasn't really been, you know, a raw exploration like I would usually do on a channel where I literally came to these from scratch, but just not, that took me, let me see, if I go to, I'll probably have to open my other, so if I go to Studio, right? Studio or YouTube. Sorry, that's not what I want to open. I want to open the other one where I'm signed up with my, so don't worry, there's nothing secret in my YouTube statistics, but if you go to the Grover's playlist. So that's Grover for NISQ machines, but like, it's 37 videos. And each video is like, you know, they go from like 50 minutes to like 10 minutes to like sometimes 1 hour. And so I wouldn't have been able to squeeze that into this 1 hour and a half session, but I just at least wanted to kind of give you the gist of what I sort of came down to with all these little explorations here and there. I think it's I don't know. I thought it was interesting to share these, and I'm definitely, you know, far away from being an expert in these, and there's much more to explore here. But yeah, I hope that was somehow helpful. I'm trying to think as I talk whether there's anything else that I kind of could share about Grover's algorithm. I think that's it really. So I don't know, any questions, thoughts, ideas? I see a question in the chat. How come the probabilities are not to 1? In which case they didn't add to 1? Was it in one of the, was it in the 4 qubits case? They definitely add to 1. It's just that the other ones were really small. So you probably weren't able to see them.
If you look at the three green bars here, it's 50, 50, 50 3 times.
Oh, those are, you mean these bars here? So those are just because these are the probabilities of each individual qubit measuring 1 or 0. So those are isolated measurements of the qubit. And this is a visualization of the state of the whole system. This is an important, it's a good question. It's an important distinction because when you take a look at a quantum circuit, you have to sometimes jump between looking at it at the qubit level or looking at it from the system level, right? And a great example for this is actually the classic, the traditional example of a Bell state, right? So if I just like the easiest form of entanglement is this one where you see that each qubit has probability of 50% of being measured into 0 or 1, right? But if you take a look at the state of the system, the only 2 possible measurements you're going to get are the 0, 0 or the 1, 1, which kind of means that if, let's simulate with a post-selection gate that we measure a 0 here, it instantly tells us that the first qubit is 0, right? So that's why these are just qubit level probabilities of being 0 or 1. Yeah.
Yeah, that makes sense. Thank you.
Cool. Yeah, I mean, you know, if I hope that at least I was able to kind of awake a little bit of you know, curiosity in at least one person in the room. So if you kind of enjoyed the chat and I was not too annoying, and you really want to, you know, hear me talk more and more, you know, really happy always to receive new subscribers in the channel, and it's, you know, it's always really really helpful to see that there are people interested in these, and that, you know, you guys are kind of really helping me push this thing forward, which, you know, it's an amazing thing, to be honest, from that side of the screen.
Can you post your channel link to the?
Yeah, sure.
Oh.
Yeah, let me see if I don't know myself. Let me see if
I can pull it up for you.
yeah.
It.
Okay, cool.
Yeah.
Thank you.
Anybody else? Here it comes. Wait a minute. Do we get an autographed copy of a video or anything? Yeah. There we go. There you go, John.
All right, thank you.
Yeah, definitely take a look. What do you got? What, 200 videos now, something like that?
Yeah, a bit more than it's like about 250 or something like that. It's I try to upload like 2 to 3 times a week. I do some of the stuff that it's not always just exploration. So I do shorter videos as well, where I, you know, invite some guests and play some puzzles, and do some stuff that is a bit more lightweight, or for people that are more like, you know, beginning their journey. But I also do a lot of really weird sometimes stuff. I have a bunch of videos on continuous variable quantum computing, which is the weirdest thing that you will ever see, which is a you know, it's a sort of an analog version of, it's not digital like in quantum computing. You have in this quantum computing version, you have zeros and ones and superpositions, but in continuous variable quantum computing, you have it's just the real numbers, right? So you're measuring position and momentum waves, and it's super funky. And so there's a lot of really niche stuff in there as well. So it's definitely not everything for everyone. Yeah, but there's definitely something interesting, I guess.
Yeah, I got to say, Daniel, I'm looking at your list here. It's been a while, ever since you know, the pandemic. I really haven't been on your channel that much, and it looks like you've changed your style a little bit recently. Indeed, you're doing interviews and all that. Cool.
I mean, it's not. I'm not fully doing interviews. It's more like I'm sending some little puzzles to people that are sort of quantum computing enthusiasts, because what I want to do is so I call these the turn the qubits off show, so to say, which is the purpose of this is to basically try to get a sneak peek of someone else's way of thinking. So I ask the guests to try to solve a puzzle, which is basically a quirk. It's a reduced version of quirk. So if I go to what is Quantum Daily, I think I'm about to release a list of a bunch of puzzles as well. But there's a if you search for qubits off, you might find a list here. Yeah, so I send the guests puzzles that look like these. So I'm just gonna pick this one, for example, and it's a reduced version of quirk, where you kind of see that you don't have all the other gates. So you have a subset of gates. You have a black box that you don't really know what it's doing, and then you don't have all the other fancy displays. And the goal is to try to turn the qubits off by sort of, you know, thinking through and applying different gates and seeing how they change the probabilities. And so what this gives you is a sort of a sneak peek into someone's way of thinking, which I think that's kind of what the channel stands for as well. It's not about really well scripted interviews. It's more about, hey, just solve these and show us how you think, right? And yeah, I've done 4 or 5 of those videos, and I think they've proven really interesting.
Yeah, in fact, I took a little bit of that idea. I had a summer camp today, so I'm teaching a bunch of junior and high school kids. and we're going through the knapsack problem. I'm working through D-Wave this past 2 weeks.
Okay.
And so I haven't done it in years, but I actually kind of took your style with the students, solving the knapsack problem in classical. We're trying to get them to understand that before we put it on the D-Wave. And boy, that's humbling. I'm used to sitting there at a bar with a napkin and working it all out, but then when I tried your style today, and boy, that's humbling, man.
I mean, it's one of those things that like it's, it feels intimate, right, to some extent, because it really exposes one's own weaknesses in terms of thinking. And but it's a really interesting experience. So I really recommend this to others as well, to kind of, not only with quantum computing, but with other topics as well. I think it's a marvelous way of learning.
Indeed. When I was, taking courses in computing, programming languages and such, it always felt like an idiot because the instructor would stand in front of the class with a scripted, the code's been worked on, prior to the class, and they just crank it out without making any mistakes, maybe a typo here and there, but on the board. But, it always amazes me because it makes the teacher look like a genius when in fact he or she, makes mistakes just like the rest of us, and the students just see this, this sequential order of creating a program.
Yeah, exactly.
And it's just so bogus that, there's tons of flaws in there. And I think, I mean, that's the brave soul to let that be exposed.
Exactly. I mean, that's, it's kind of what you got today here. It's really a, sort of the final version of where I got, right? But if you really want to see that process, go and take a look at those 37 videos. I mean, at least 2 seconds of each video. I need some more. I need some more watch time. So if you guys can just put some videos in the background, that's gonna. Not kidding. But the idea is you've got all those 37 videos in there that take you from scratch to what we've seen today, right? And yeah, that's quite amazing.
A social scientist or a psychologist would probably enjoy it because you can see, the go back and step back, go forward, go left, wrong turn, etc.
I wonder what would happen if you would feed these videos into a machine learning algorithm.
Yeah, robot would be going in circles, man. But end up in the right place, right?
Exactly.
Anybody else? Well, we got Daniel one-on-one here. Any comments? How's the weather in your respective homes right now, people? Anybody? Okay, well, if I do my calculations correctly, what is it, like 1:30 there, Daniel?
Exactly.
All right, well, we'll get out of your way then if everybody's going to be gun shy here. Thank you very much. Definitely appreciate it.
Thank you for offering the possibility of joining you guys in this Quantumapalooza concept, which is it totally flew under my radar. I really was not aware of all that until you reached out, and there's definitely a lot of stuff going on in there.
Yeah, well, we have secret signals and everything like that too. It would take you a while to understand, but no, it's Quantumapalooza was originally 3 weeks of just content every day from the Philadelphia Harrisburg, but now I'm just keeping track of everybody else's content out there in one place because there's a hell of a lot going on live. So anyway, I'm gonna start feeding it to some of the online sites as well. Get the the work leveraged. But anyway, okay. Well,
cool.
We got a quiet group here, man. I don't know what's going on. I think it's
too much at once, I guess.
Yeah, maybe so. Maybe so. All right, really Daniel. Thank you very much. Everybody else, we'll see you next time. And in the next, hey, don't forget, people. There's a conference going on right now, all online. Look at the Quantumapalooza site. All those speakers, it's all morning U.S. time. They're all free, and it's you know, usually that conference costs what, $700-800 to attend. So we're able to watch it for free. So take a look at some of those talks. Good night,
Also,
everybody.
if you sign up for the conference, they'll send you the links to the recordings.
Yeah, I mean, just sign up, and the links are all in one email, and you just click and kind of go. Thanks, Tom. See you guys later.
See you.
Bye-bye, George. See you around. Amir.
Bye, everyone. And
Bye,
just so
David.
to be
Thank
aware,
you.
Bye.
those links for the conference are only active for 3 weeks. So you've got 3 weeks to look.
Ah, thanks. Do you know what they're going to do with the recordings?
Well, they've in those emails, it says you can look at the recordings for 3 weeks, and then it doesn't say thereafter, but they may disappear.
Okay, well, 3 more weeks of binging then. I'm burned out. See you all. Thanks, Amir. See you all later.
Bye.
Good to see you all. Happy computing. Thanks again, Daniel. Appreciate it a lot.
Thanks.